Okay, the next video in our sequence, of videos about financial applications of geometric sequences, and this time we're going to look at regular payments. So regular payments are situations where compound interest is combined with equal payments. So we've got a compound interest scenario and also equal payments. These equal payments are occurring at regular intervals of time. They're happening regularly. And there's lots of real-world examples: superannuation, loan repayments, annuities. Okay, and so they can be based on wealth accumulation or security, like super and annuities. It can also be based on, or debt extinguishment. So that's your loan repayments there. So it's a similar scenario, although there are some differences, as we'll see in this video. Now, in the real world, things aren't always yearly, but in our examples and our context, we're going to focus on yearly payments. But you can have monthly, quarterly, fortnightly. There's other intervals possible, but we'll just keep it relatively simple with yearly. That matches what we've been doing with geometric sequences. Alright, consider a situation where Sophie wants to retire in 15 years and she decides to deposit $6,000, not $6, that won't get her retirement, $6,000 into the bank start of each year until her retirement. Alright, so it's not one deposit of $6,000 and then 15 years happens. There's one every year, and they accrue interest at different times for different durations. So this is a more sophisticated situation. It's a bit like a whole lot of little investments going on at the same time. We've got an interest rate, assuming that stays constant for the term of this. This is pretty much basically what's called an annuity, this one. It's like a savings plan. And assuming that stays consistent at 6% per annum, compounded annually for this annuity, what will the account balance be when Sophie retires at the end of the 15th year? Now, at the end of the 15th year is a time of 15 years from the start. Because if we look at these blue, see the light blue dots there, if you can see the cursor, you can see the light blue dots. So that would be first year. So at the end of the first year, you've gone 1 year. Second year, at the end of the second year, you've gone a total of 2 years. So at the end of the 15th year, don't get confused, it's not 16, it's 15 years in total. Before we look at a formula for this, we can see what's going on. So if we start right now, bang, what Sophie does immediately is put $6,000 in. That $6,000 then goes on a little journey, and you can see the blue line with the little brown dots on it now, and that's its journey. It's a bit like its own little investment, and it does 15 years of work at 6%. And we know how to work out how much that part of it accrues to. Okay, that part of it there accrues is 6,000 times 1.06 to the 15. So that little bit does that job. But not only that, we have, after 1 year, another 6,000 gets deposited in, and it goes on its own little journey too. But it's a shorter journey. It starts there at year 1 and it goes along, and of course at the retirement point there, it's done 14 years. So it'll be doing that job, raised to the power 14. So of course that'll be a slightly less amount of money. But these two are both adding to the value of the annuity at retirement. And of course that keeps going. There's another one and another one and another one. So the next one is 6,000 times 1.06 to the power 13. Okay, so where does that end? At the start of each year, she puts those groups of 6,000 in. When will the last one be put in? Alright, it will be put in. So that's the first time at 0. So that would be the last one at 14. That'd be the last chance to put in that. So that'd be the last one. 6,000 is put in here for the last time. Alright, because if 0 is the first year, beginning of the second, let me try that again. At time equals 0, it's the beginning of the first year, we've got the first 6,000. At time duration equals 1, we've got the second. At time duration 2, we've got the third. So at time duration 14, we've got the 15th and final payment. And now what will that investment look like? Because it'll be the end of this sequence. See, it's a sequence, they're terms in a sequence. Alright, and there's a bunch of terms in there. And the final one will be 6,000 times 1.06 to the 1. You can see that because you can see that on the number line there. Alright, on the timeline, money line, it's got a year to go. And also you can see it here because we need, as we said, we need 15 of these, and the last one would have to be 1 because you can tell the indices equate to the number of terms there, right? Now this here is a geometric sequence. So the sum of the terms in a geometric sequence, or a series in other words, we've seen that before. Okay, we've seen that before, and remember the terms in a sequence, geometric sequence all added together, or a series in other words, looks like this. Sorry, let me fix that. Okay, the series looks like that, and that's from our previous work. So in a regular geometric sequence, A is the starting value, whereas we've got this. Okay, so that's our starting value there. So what is that starting value? It's the principal times the rate. And the rate is to the power 1, so we can just say it's principal times the rate. So the second term, so what I'm doing is just finding equivalence with our general expression for a series. Next one would be 6,000 times 1.06 times 1.06, or 1.06 squared, as you might have deduced. So that's 1.06 squared, isn't it? So it'd be P R, that and that, times R again. Alright, because that's like this term here, because it's P R times R, isn't it? So it's like A times R. And we finish it off as per the general series. So to come up with a formula that can be an equivalent to that, and A stands for accumulated amount, we can see a few things here. The first term was just PR. Normally it's called A. So instead of having A out the front, we have PR. And R is still the same. It's that growth rate, because as we went from one term in the sequence to the next, it's multiplied by R, so that's still the same. The number of terms is still the same as well, because you can see we have a correspondence there. And I've actually just spotted a little error there. I wonder if you spotted it before. That should be an N. There's a reason why it should be an N, because if you look at the correspondence here, that's that's a 1 there, and that's a 2, that's a 2 there, that's a 3, that's an n minus 1, that it should be an n. Okay, we've got the same number of terms, however. If we kept going and found the derivation of the rest of the formula, which is actually done in an earlier video, we would actually get all the other elements would come out the same, and you can go back to that earlier video and try that for yourself. So we actually have a formula here for any situation like an annuity or superannuation payments into a superannuation fund where the amount is growing. Okay, and so this is a case of a series because it's the sum of the elements in a sequence. Now that we've identified that these elements here, so if we were to the above situation with Sophie could be calculated in a far more efficient manner by looking more efficient than this by just subbing into this formula now that we've given our chance to establish it. Okay, so let's do that then. We just need to identify all the parts of the formula, so let's do that. So the principal, the growth rate. Alright, well the principal is actually the payment here. So it's the regular payment. So it's probably not correct to call it the principal any longer now that we know it's the regular payment. Alright, so we were using it as a principal up here, but really it's more accurate to call it a regular payment. So that's your regular payment. In this case it's $6,000, and we've got the interest rate, which is the growth rate. Okay, it's actually not the interest rate, it's 1 plus the interest rate over 100 like we've been doing previously. So that's the growth rate of the money, or the common ratio. So that's 1.06, and n is the number of payments made, and it's also the number of years as well, and that's 15 in this case. And we can just sub that in, and lo and behold it'll get us the answer more quickly. So 6,000 times 1.06 times 1.06 to the 15 minus 1, and that's over 15 minus 1, which is 14, and then we calculate that one. Oh sorry, I goofed then, I put the wrong thing on the denominator. It's r minus 1, I accidentally put in n minus 1, that makes an enormous difference. So it's r minus 1, so 1.06 minus 1, which will be 0.06, apologies. So my calculator is saying that we've got $148,035 and an awesome 17 cents. Okay, so depending on what Sophie's goals were and what sort of lifestyle she wants in retirement and assumed longevity of life, etc., whether she already owns stuff or still paying stuff off, she can work out whether that's enough money, and she might have to start either upping the ante if it's not, putting in bigger payments of $6,000 if she can afford it, and where the other thing she could do is put off retirement a bit longer if she needs to save it up. So in the next video we're going to look at the opposite situation where we're borrowing money and we're going to be repaying $6,000 at the end of each year. Alright, and we're going to see how that differs to the scenario here. There are some